So today we are going to get away from HVAC, sort of, or I guess it would be more appropriate to say we're going to take a deeper dive onto one specific part of HVAC, and that's on fans and motors. Everywhere you look in a building, you're going to see motors. And in HVAC specifically, 95, 99% of the time, they're going to be driving fans that move air through the building, your heating and your cooling airflow, or they're going to be driving pumps to move water through your building. Today, we're going to focus on the air side of things and really focus on fans. We'll come back to pumps down the road. Almost every HVAC fan we look at are what are called centrifugal type fans. And all that really means is that they create air movement through creating a pressure differential. And I'll explain how that works here in a second. The idea is that within the fan is what's called an impeller. And that impeller is going to spin on a motor to make that air move, which I'll get into more depth here in a second. But the idea is that that fan impeller has to overcome the resistance of the ductwork and anything else that could be in that ducted system between the supply side of this fan and the return side of the fan. So the ductwork in your building, that's all going to be resisting airflow. I mean, the longer the duct runs you have, the more resistance will have to be overcome by the fan to move the air. And that's all just due to the friction of the air moving through the duct. So to get over that resistance, the fan has to create a positive pressure to overcome that friction throughout the entire ducted system. So this is a basic fan schematic. We have the fan casing, just the thick black outline there. And then the red wheel looking thing, that's essentially like a paddle wheel. So throughout this impeller, radially, you have all these paddles. And as this impeller spins around, what happens is that pushes air outward from the impeller. And as that air is pushed outward, that induces a negative pressure on the inlet. So imagine a hole in the fan right here, dead center of the impeller. And so as it spins, pushes air in an outward direction, which essentially creates a vacuum. And so that vacuum that's created will want to suck in air wherever it can, which is going to be in the center of the impeller. So what that means is that going into this fan, this will be the negative pressure point because it's sucking air in. And then on the outlet of the fan, on the outlet of the impeller, that's going to be our positive pressure point. And so if we have a positive pressure point and a negative pressure point, what that means is if you took a pressure reading device and you plugged it in on each side of the fan, you would read a differential pressure across the fan. So you'd have some positive pressure on the outlet and some negative pressure on the inlet. And this is what that would look like in a real fan. So we have the fan casing that houses the impeller inside with the little blades or paddles, whatever you want to call them. And as that spins, that's going to induce air through the inlet and then discharge on the outlet. And so how do we measure fan power? So this was a poor sap on Who Wants to Be a Millionaire. I gotta imagine This guy used a lifeline. I have to imagine this 29% of people have to be trolling him a little bit. So, of course, we measure fan power in llama thrust, right? No, we don't. It's all about horsepower. So the motor horsepower requirements, they're all going to depend on a few different things. So one of the major things is how much air is our fan moving? What is the airflow of that fan? And we're going to measure that in cubic feet per minute, which I think I've mentioned a couple times before, but it's mostly been in passing. So if your fan is moving more air, then more horsepower is going to be required. And I hope that just makes intuitive sense. Another major component of this is the total static pressure. And that is, what's the pressure differential across that fan that's going to be needed to overcome that system resistance? What will it take to move a certain amount of airflow from the start of that fan through the ductwork, through the space, through the return duct, and then back into the unit? And so this is typically measured in inches of water column. You could measure it in other pressure units, but in the calculations we use in this industry, it's always in inches of water column. And if you have longer duct runs, or if your duct is restrictive, meaning what if your ductwork is undersized for the amount of air you're moving? Well, that means it's going to be moving faster, which means there's going to be more friction. So if you have longer runs, or if you have more restrictive duct runs, that's going to require more pressure from your fan, and the more pressure output from the fan you need, the more horsepower you're going to need. The last thing that plays into this is just what I'm generically calling the system efficiencies. And I'll go into more on this here in a minute, but that includes fan efficiencies, motor efficiency. There can be other losses. If you have a belt-driven fan, then there are some losses associated with that belt drive system. And these efficiencies are always measured from 0 to 1, or 0% to 100%, because you can't have a motor that's more than 100% efficient. If you have lower system efficiencies, then that's going to require more horsepower. There are a few different ways we can express a measure of horsepower. The first one is what's called the air horsepower, and that is based on the airflow in cubic feet per minute multiplied by the total static pressure in inches of water column. So there are those two major items. How much air are we moving, and how much pressure do we need to output to get it through the system? And then we have this constant on the bottom, 6,356. And that is just a constant that's based on the specific gravity of air. That's also assuming we're working with units of CFM and inches of water column. If for some reason you were using different units, you'd have to come up with a different constant in the denominator. But in the industry, we use CFM and inches of water column. And so you can see more airflow is more horsepower, more pressure is more horsepower, and vice versa. And air horsepower could be described as what does that impeller need to output to deliver whatever CFM we want at whatever design static pressure is needed. Another way to word that is, what's the useful delivered work? And so this could be comparable to thinking of a load or an output of other systems. This is the final output of a fan. How much air and how much pressure. And that's the impeller's one job, to deliver that CFM at that static pressure. But these impellers, they're not perfect at taking this motor input energy and turning it into useful work. So if the motor that's driving our impeller, let's say that motor is putting out 10 kilowatts of power into our impeller, but maybe only 7.5 of that actually gets transferred into something useful. So the energy or power you're putting into spinning that impeller, that's not a perfect process. So most of that will become something useful, but some of it is just going to be lost as heat, just because every process we have is inefficient to some degree. And so that inefficiency I'm talking about of the impeller, we call that the fan efficiency. And that brings us to the next measure of horsepower, which is called the brake horsepower. You can see it's the same exact equation, except now we've factored in our efficiency of the fan impeller itself. So the brake horsepower, BHP, that is all about the motor shaft. What does our motor shaft need to output to deliver, again, whatever airflow we need at whatever static pressure we need? But now we're accounting for the impeller losses. And because the efficiency of the fan is always going to be less than 1, our brake horsepower, the output from the motor, is always going to be greater than the air horsepower, which is our useful output, every single time. And we can take this one step further. Motors aren't perfectly efficient either. So if we feed that motor 10 kW to the motor itself, well, how much of that is going to turn into something useful at the motor shaft? Because that's not a perfect process either. And those inefficiencies are the what are called the motor efficiency. I mean, who could have guessed that? And that brings us to the last measure of horsepower, which is descriptively called the motor horsepower. And so that's the same equation again, except now we are factoring in that motor efficiency. And this motor horsepower, this is our total electrical input. And if we are thinking about how much power and energy is this fan going to use, this is what it all comes back to. It comes back to, what do we need to feed the motor? Because that's what's going to require the most power. And then as it get down the line, we'll have some losses at every step. And so you might notice that we have this cascading effect. So we started with air horsepower, which was just divided by the constant. And now we've added in the fan efficiency, and now we've added in the motor efficiency. So if you think back to the second lecture, I think, where we talked about series efficiency, this is exactly what's going on. And there can be some other components here, some other things that cause losses between where we're starting our process and where we are ending our process. So for example, later on today, I'm going to talk about a device called a VFD, a variable frequency drive. If you have a motor with a VFD on it, that has some losses too. And so you would need another efficiency factor down here to account for that. So let's look at a quick example here to kind of illustrate how all of these metrics play into each other. So let's say we have our fan here. This impeller is driven by this motor. Assume that that's the motor shaft poking out of your screen. And the designer figures out, I need this fan to move 10,000 CFM of air at 2.5 inches of static pressure. The fan efficiency, or the impeller efficiency, whatever you want to call it, is 70%. So that means for every watt you put into spinning that impeller, you'll get 0.7 watts of useful output out of it. And let's say the motor efficiency that is driving our impeller, that's 90%. And now let's calculate each of our horsepower metrics. So the air horsepower, that is simply based on airflow and static pressure. That's it. So you calculate that, and it's 3.93 air horsepower. So that's the useful output. That is what we are ultimately getting out of this thing. But then if we want to figure out the brake horsepower, if we want to know, well, how much power does our motor shaft have to output? Now we factor in our fan efficiency of 70%. And so our motor shaft has to output 5.62 brake horsepower. So the motor shaft outputs 5.62, and then we get 3.93 out of it in the end. And if we take that one step further and try to figure out our total electrical input at the start of this process, now we factor in our 90% motor efficiency. And that ends up being 6.24 motor horsepower. And that's our final electrical input at the start of this process. So every step in here has some losses. And at the end of the day, we are paying for this 6.24 motor horsepower. That's how much electrical power we need to run the motor, which then runs the impeller, which then gives us something useful at the back end. We are putting in 6.24, but only getting 3.93 of useful output at the end of the day. And that's because those losses, when you have multiple processes in series and you multiply those inefficiencies together, it ends up being a pretty big hit. And like I said, there could be other things between the start and the end that would also have losses. Once you know the motor horsepower, you can convert that to kilowatts. It's a simple conversion. This was even on the Who Wants to Be a Millionaire picture earlier. But if you take your horsepower, multiply by 0.746, that will give you motor kW. Once you have that, all you need to do is multiply that by your run hours to get to kilowatt hours. And that shouldn't be any surprise. I mean, we've talked about that in the past. But when you're selecting motors, typically, well, really always, they come in specific nominal sizes. So that in that previous example, we said, well, we need a 6.24 motor horsepower motor. But you can't just go to the store and buy a 6.24 horsepower motor. They make them in specific sizes. In this case, we'd have to upsize to the next size up, which is 7.5. And then the motor will just be a little bit oversized. And that's okay. In fact, virtually every motor out there is oversized to some degree, or at least it should be. But keep in mind, the motor electrical input, which also equates to energy use, is so much more dependent on the load that it's serving. So that CFM and the total static pressure, that is what is going to drive the energy use of that motor much more than the nominal horsepower. So if you have two 15 horsepower motors that are sitting right next to each other, but are serving different loads, just because they are 15 horsepower motors doesn't mean they're using the same amount of power when they're running. If one of those motors is oversized or undersized, they can use drastically different amounts of power. What does change though, with how motors are overloaded or underloaded. What does change with that is the motor efficiency. And motors, they like to be loaded. If you have a motor that's way oversized, then the motor efficiency is going to go way down. And as a side note, if you think back to when we were talking about utilities, the power factor also goes down. And if your utility bills you for a low power factor, then that could be a problem if it's a very large motor. But generally speaking, motor efficiency, as long as that motor is loaded above about 60% of whatever it's rated for, generally it's okay. But once you start to get below that, the efficiency starts to fall off a cliff a little bit. Although bigger motors are better about this at these lower loads than smaller motors. And an important note here, just because you have a low motor efficiency does not necessarily mean more energy use, which might sound weird. But again, it's all about that load that's being served by that motor. To illustrate this, let's say we have two motors. They're both the same nominal horsepower, but they are serving different loads. So motor 1, motor 2, these are both 5 horsepower nominal motors. But the first motor is moving a fan that is moving 6,000 CFM of air. The other one is moving 4,000 CFM. So the first motor is moving 50% more air, and it's also moving it at more static pressure. So 2.75 inches versus 1.75. Let's say they have the same 75% fan efficiency, but what if that first motor has a motor efficiency of 88%, and the second one is down at 72%. So between these two motors, there's a fairly drastic difference in the motor efficiency, and this has to do with how these are loaded. So what this would tell me is the first motor is probably appropriately loaded, and the second motor is probably underloaded. If you run through the calculations to figure out how much power each one of these would be drawing, that first motor would require 2.93 kilowatts, and that second motor would require 1.52 kilowatts. So that second motor is using almost half of the power when it's running. So motor 1 has better efficiency. If you're just focused on the efficiency part of that equation, yeah, it is more efficient. But because the load it's serving is greater, more air, more static pressure, it's still going to use a lot more energy, almost twice as much. Motor 2 is way oversized. It's a 5 horsepower motor, and it's only serving about 2 horsepower load. And so the efficiency is a lot lower, but it's still using a lot less power and energy because the load is smaller. So better efficiency, at least if you're looking at the motor efficiency, does not necessarily mean less energy, which seems counterintuitive. It's all about the load that it's serving. And so this is to help illustrate that just because that's a 5 horsepower motor you're looking at, the amount of power that is going to draw when that thing is running, you have no way of knowing just because it's a 5 horsepower motor. Here's an example of how the efficiency kind of drops off when motors are underloaded. I mentioned earlier that larger motors tend to be better about it. So the 75 to 100 horsepower efficiency line, and you can actually see 80%, that's kind of the sweet spot right there, 70-80% loading. But it maintains pretty good efficiency even all the way down to 20% load. But if you look at the 0 to 1 horsepower motors, you can see that that drops off a lot faster. So larger motors tend to be better about it. I'm not entirely sure why. Maybe it's just a function of, well, if it's a larger motor, it needs to be built a little more robust. I don't know, but that's the way it is. Here's a list of nominal motor sizes. So if you were to go out and buy a motor, these are the sizes that would be available. You can see in the smaller range, they have some pretty small jumps, half horsepower, 1, but then it starts to spread out a little bit. And eventually you're seeing 5 horsepower jumps. And then by the time you are in the hundreds of horsepower, you start to see 100 horsepower jumps. For reference, I think the largest motor I've ever been involved with on a replacement was 250 horsepower. And that was for this was out at WSU. They have this central steam plant that serves steam through the whole campus. And they have, in their boiler plant, they have 3 monster steam boilers that are about 3 stories tall. You have to climb up a bunch of ladders to get up to these motors. But that 250 horsepower motor was just for the combustion air, for that gas-fired steam boiler. And that's by far, that's the largest motor replacement I've ever been involved with. Normally in HVAC, we're in the range of 1 horsepower to probably 10 to 15 horsepower. So that's comparatively a lot smaller. So that's some basics on motors. So let's shift gears a little bit. We're going to talk about fan speed control. Several of the HVAC system types that we've talked about are what are called variable flow. And we vary the supply of airflow depending on what that system needs. So the most common example would be a single duct VAV system, which VAV stands for variable air volume. So it's right there in the name. That tells you the air volume that fan's going to move is going to vary depending on the active conditions of the building and all the spaces that system serves. And there are several ways in which we can vary flow through a fan. The first most basic one is what's called a discharge air damper, which is kind of a crude method. I think I used this analogy before, but it's kind of like being on full gas and pumping the brakes. Basically what this looks like is on the outlet of the fan, you have this damper that partially closes, which effectively makes more resistance in your duct system. And by adding that additional resistance in the system, that has a corresponding reduction in airflow. So you're effectively just increasing the pressure requirements to move your air, and then you see a corresponding reduction in airflow. This is by far the worst way to do it, but it does work. At least it works to vary the airflow. It doesn't do a whole lot in terms of actually saving energy. So this is what that would look like. If you imagine these damper blades all kind of turning in unison. So if we wanted a reduction in airflow, we would start to close these dampers and just create more resistance in the duct. Now, obviously, we can't close it all the way, because then you will you'll do what's called deadhead the fan, because the air is not going to have anywhere to go. So there will be some minimum position, but it still does give some amount of airflow control. This, excuse me, the second method is using what's called inlet guide vanes. So on the fan impeller inlet, so where we're pulling in air to the center of the fan impeller, you install these variable pitch blades that open and close in unison in a radial fashion. So this is what that looks like. So imagine sticking one of these right over the impeller inlet. So this is where the air would be going in. And so all of these blades, they open and close in unison. So right now, this would be about a full open position. So this would have the most amount of airflow and the least amount of restriction. But then you can close it to a partially closed position, which will reduce airflow. So these are called inlet guide vanes. So that either restricts or allows air to go into the fan impeller. But the other unique thing about this is when those are in a partially closed condition, so if these are partially closed, what ends up happening is as the air moves through this thing, it actually pre-turns the air. So you might have noticed that with those fan impellers, the air actually has to change direction. So it goes into the inlet, but then it has to go outward radially to get to the impeller where the impeller is spinning. What this does is as the air moves through these blades, when these are partially closed and they're at some angle, that will start to pre-turn the air in the direction that the impeller is spinning. And what that does, well, it does two things. As those close, that does create a restriction. So that does reduce the amount of air that's going to go through that fan. But at the same time, as those turn and create that restriction, they also take a sharper angle and pre-turn the air more. And by doing that, that reduces the load on the impeller by reducing the total static pressure requirements. So it's a combination of things. We're reducing airflow, but we're also reducing static pressure. And at the end of the day, it's actually not terrible in terms of energy savings. It's not the best, but it's certainly much better than the discharge air damper. So there's another example of what that would look like. And this link just goes to that YouTube video I just had up. The next one, I mentioned this earlier. This is a variable frequency drive, or a VFD. And what this does, this is an electrical device, whereas the discharge damper and the inlet guide vanes, those are mechanical devices. You're moving those dampers and imparting a mechanical effect directly to the fan system. A VFD, though, is an electrical device that allows you to directly influence the motor RPM. And if you can change the motor RPM, you are also changing the speed at which that fan impeller is moving. Standard AC power in the United States is at 60 hertz. But what a VFD does is it takes that 60 hertz input and then it can decrease, or it can actually increase the frequency as well to a different hertz. So as an example, if we went down to 45 hertz, that would move the fan at 75% speed. If we went down to 60 hertz, that would be 50% speed. And we can go anywhere in between that as well. So whatever speed we want that fan to run, we can do it. Well, as long as we don't go too low. Right around 15 hertz or 25% that is generally the low limit. And you start running into some operational issues if you keep trying to push that VFD to a lower speed. And a VFD, this is the best option for reducing fan energy and larger motor sizes. So if I had a 50 horsepower motor that I wanted to convert to a variable system, a VFD is what would do the job for me. But even though it's great, there are still some losses here. So if we think back to our horsepower equations, if we had a VFD on the fan, we would need a VFD efficiency factor in there. And usually it's right around 5%. So it's not terrible, but there is some inefficiency that has to be factored in as a result of the VFD. This is my very basic schematic of a VFD. So it's taking that 60 hertz of electrical input, and then it's sending it out at 40 hertz, which in this case would be 67% speed. So it's taking that electrical signal and then playing with it and only outputting the frequency we actually want. And the last speed control option is what's called electronically commutated motors, or EC motors. This is a newer technology. Well, sort of. EC motors have been around for a long time, but generally they've been limited to very small motors. So EC motors, these are direct drive, meaning the fan impeller mounts directly onto these motor shafts and then spins. Whereas in a larger fan system, a lot of times you would be using belts to indirectly drive a fan from the motor shaft, which I think I talk about more in the follow-up lecture. So these are direct drive motors, and they're DC power as well. So they're taking AC power because that's how we power everything, but built into the motor is a converter in order to turn that into DC power. So the motor shaft mounts directly to the impeller, like I stated, which from an efficiency standpoint, that means that you're not going to have any of the inefficiencies associated with using belts. And from a maintenance perspective, now you don't need to have to worry about replacing those belts when they fail. So that's a nice little bonus. And with EC motors, these are able to adjust the fan RPM directly through an onboard controller without a VFD though. These are effectively doing the same thing as a VFD in that they are directly modifying the fan speed, but they can do it without a VFD. So it's got an integrated onboard controller to get that power conversion and to provide that speed control. So these are more efficient than other motors. And really, it is the best option for speed control if available, which that is a big caveat if EC motors are available. Right now, these are only available in smaller sizes. The energy code now in Washington basically says if you have a motor that is 1 horsepower or less, you have to use EC motors. They require it. But now we can get 3 horsepower, 5 horsepower motors or comparable sizes in an EC version. So they are getting bigger. It's kind of like when we were talking about LED lighting. LEDs have been around for decades, but for a long time, they were really only used for the little blinking lights on your computer, on your motherboard. But now, over time, the technology's gotten better. The technology's gotten less expensive. And so now we see LED lighting used as our primary lighting fixtures. EC motors have kind of taken a similar path where they've been around forever, but the economies of scale really don't work in their favor for larger motors, or at least they haven't until now. If we're talking about modern HVAC systems, it's pretty much done exclusively through VFDs or EC motors. It just depends on what size of motor you're dealing with. Discharge air dampers, inlet guide vanes, we don't really see these on new systems. I've never designed a system where we've installed new discharge air dampers or inlet guide vanes, but I've been involved on a lot of projects where we've taken them out and converted the system to say a VFD system. So it's still important to know how they work. And if you are doing an energy audit and you walk into a building and their HVAC technician and they say, well, we got inlet guide vanes on these air handlers, you still need to know what that means and how they work. So we'll have more to come next lecture in part 2. Any questions on this or homework or anything else? All right. I'm happy to stick around. Otherwise, have a good weekend, and I will talk to you next week.
Thank you.